So, so anyway, what I want to talk about today is quantum correlation sets. There's been a lot of development in this area, and one of my favorite things to talk about. And so, the membership problem part here is just to give us some focus for the talk. So, so what I want to do is give you some history behind what quantum correlation sets are, and then what the recent developments in them have been. So it's not going to be a too technical talk, but I do want to talk about some of the basics because they're pretty easy. And you know, it's a math talk. We should try and understand the math instead of just everything being at a high level. So I hope it's okay to talk about some of the basics here. And if you'd like to tune these out, I can say most of the talk should be understandable without actually having to understand any of the technical details of what I'm going to say. So if you feel you're more in the mood for a talk with no technical details, just let those kind of wash over you when I'm talking about them. But anyway, I want to talk about some of the basic rules of quantum mechanics just to explain what a quantum correlation set is. So the simplest possible rules are, first of all, that a physical system is a Hilbert space, which whenever you see H, that will usually mean a Hilbert space. The state of the system, that's like the parts of the system that can change. So if it was looking at my window here, it's pretty snowy here. So maybe the system would be the park that's adjacent to my house, and the state would be all the snow and the arrangement of everything inside the park, how that's arranged. So the state of the system is given by a unit vector in the Hilbert space. And then if we want to take two subsystems, let's say H1 and H2, and combine them into a joint system, we do that by taking the tensor product, H1 tensor H2. So that's something we kind of do all the time. If you want to think like H1 could be a lab on one floor of a building, and H2 could be a lab on a different floor of a building. If we want to talk about the joint system for both floors together, we would do that by taking the tensor product of both of those Hilbert spaces.
And do
And
you
this is
worry
called
about completing the tensor product?
yeah. So this is it's a tensor product of Hilbert spaces. So you would complete it. Yeah. So this is called the tensor product axiom. Although about completing the tensor product, I am going to spend most of the talk talking about finite dimensional Hilbert spaces. So then you don't have to worry about it. But yeah, so for when I'm talking about infinite dimensional Hilbert spaces, then you should complete it. So we'll talk about some other replacements for this, or one other replacement for this axiom, about 2/3 of the way through the talk. Now, what about the state of a joint system like this, H1 tensor H2? So the state of such a system could be a product state, U tensor V, for states. By the way, I'm going to say state just synonymously with unit vector. So for states U in H1 and V in H2. But the system can be in other states. So we know if you have a tensor product that not all the vectors in a tensor product are of the form U tensor V. And so those other vectors, if they're normalized, can be states as well. So you could have something like 1 over square root 2 U1 tensor V1 plus U2 tensor V2 for, let's say, so for some orthonormal vectors U1 and U2 in H1 and V1 and V2 in H2. And really any unit vector in this tensor product could be a state of the joint system. And so a state which is not a product state is said to be entangled. So if you ever read about entanglement in the media or anything like that, all that it's talking about is the fact that you can have states which aren't product states in a tensor product. Now, one of the most important unstated rules of quantum mechanics is that we can't look directly at the state of a system. So it is or can be modeled as a unit vector, but we don't get to see what that unit vector is at any point. And that's because when you talk about looking at something, that's like doing a measurement. And in quantum mechanics, there are rules for what a measurement is. Measurement can only happen in specific ways. And so, and by the way, I'm talking about kind of just to keep things simple, some very kind of the easiest versions of the rules. So there are more general forms of states and there are more general forms of measurements. But so just an easy to understand version of what measurement is in quantum mechanics is what's called projective measurement. So a projective measurement on a system H is given by, first of all, a set O of possible outcomes. And usually we think of this set as being finite. And that's because when you think about what you have in a measurement, so I should say in quantum information, we usually think about this set as being finite. And that's because when we think about what a measurement device is, maybe it's measuring something we think of as a real number and recording it in a computer, but that computer can only ever hold a finite list of values. And so any kind of measurement device that you can imagine eventually is saying, sorting things maybe into buckets. It's never really has a continuum of possible measurement outcomes. So we normally think about a finite set of measurement outcomes in quantum information to match that physical fact. And the other thing, maybe the more important thing, is a complete family of orthogonal self-adjoint projections indexed by this set of outcomes. So what that means is, by the way, does my mouse show up on the Zoom? Yeah, okay, good. Let me know if it's not showing up and I can share my desktop instead of my window. Okay, so orthogonal self-adjoint projections means that so projection means that PO squares to itself, and self-adjoint means that PO is equal to PO star. So I should say these are operators on the Hilbert space H. And then complete means that when we sum them up, we get 1. And I should say, I really should have put this in here. Orthogonal means that if we have 2 possible outcomes, O and O prime, PO times PO prime is equal to 0. Technically, for operators on a Hilbert space, that's implied by these relations, but it's good to have in mind that that actually holds for these operators as well.
Did you define what you mean by an outcome?
Yeah, so an outcome is just what the measurement actually gives as a result. So I'm actually going to say a little bit about that here, but just to fill in what the outcome part of that means is we're going to do some measurement, and maybe we'll measure, it could be a 2 outcome measurement. And so the outcome set O could be, I think just on the next slide, we're going to do this. Yeah, we'll get to that in a second, but it could be like the set 0 and 1. And that would mean when we do the measurement, I always just think of it like there's some box and it's got a screen and a button on it, and you hit the button to perform the measurement, and then the result flashes on the screen. And so the outcome would either be a 0 flashing on the screen or a 1 flashing on the screen. And that would be the outcome of the measurement.
Thank you.
So how to interpret, so that's how to interpret this first part. It's a great question. And the thing is how to interpret then the second part of this with these self-adjoint projections. And they tell us the probability of getting different outcomes based on the state of the system. So the result of the measurement will depend on the state of the system. That makes sense if we think about what state is supposed to mean. And so if the system is in state U, we get outcome O with a probability which is the norm squared of PO times U. And if you think about what that is, that's the inner product, because this is a projection, that's the inner product of U with PO U. And so the sum over these numbers will actually be the norm squared of U. And the norm squared of U is 1. That's why we required U to be a unit vector. So this is a probability distribution on the set O. And then the other thing that happens with this measurement is that after we measure, the measurement itself could affect the state of the system. That's one of these kind of features of quantum mechanics that we're talking about. Typically systems which are so sensitive to interaction with the environment that just measuring them will affect them. And so encoded in this definition of what a measurement is a rule for how the state of the system changes when we do a measurement. And how that works with a projective measurement is that the state of the system will be PO times U, except that we have to normalize it to be a unit vector again. So we divide by the norm of PO times U. And of course, if this is 0, that would be an outcome that never happens. So we just say there's no rule for what happens in that case. It happens with probability 0. So any outcome that happens with probability greater than 0, this will make sense. Okay. Now, again, this is part of the technical details that if you prefer not to think about, that I think you'll be able to understand the rest of the talk without it. But it's kind of neat just to see an example because these are very concrete things we can work with. So let's say we take H to be the Hilbert space C2, which is what's called a qubit register. And let's take U to just be a simple unit vector in there, 1 over square root 2, U1 plus U2. And then let's let P0 be the projection onto E1 and P1 be the projection onto E2. So if we measure U with this complete family of orthogonal projections, what we get is 0 with probability, which is the norm of P0, the norm squared of P0 applied to U, which is 1 over square root E1. And of course, the norm of that vector is a half. So we get 0, which is the index of that projection with probability a half as the outcome of the measurement. And then the state after measurement will be E1 over square root 2 normalized, so just E1. And then for outcome 1, it's the same thing. We apply P1 to U, and we get E2 over square root 2. So that happens with probability a half. We should know that that happens already because there's only 2 possible outcomes for this measurement. So if one happens with probability a half, the other one does as well. But the output state will then be that vector normalized, which will be E2. Okay, so let's do this again. Let's see what happens if we do it with an entangled system. So let's say we take 2 different qubit registers, so H1 and H2. So you could think of these as being maybe 2 competing labs, one each on a floor, one on floor 1 and one on floor 2. And they're each doing measurements on a qubit register. And the state, somehow they've become entangled. I've written down a state here, which is an entangled state on the joint system. So this is in H1 tensor H2. So 1 over square root 2, E1 tensor E1 plus E2 tensor E2. And let's say we do the same measurement as before, just on C2. And what I want to do is just measure, so I'll say that in a second, but I want to measure just the first register maybe, which should make sense, right? We should be able to do a measurement in one lab and not change the second lab. But to do that, I need to tell you what the rule is for how to combine measurements in separate systems. So here's how that works. It's very intuitive. If you've got a measurement operator on H1, let's call that P sub X with outcome set O1, and you've got another measurement operator Q, QY for Y and O2. Okay, so then what that means is that we're doing a measurement on H1 where the outcomes come from O1 and a measurement on H2 where the outcomes are in O2. So if we're doing those measurements at the same time, like these 2 labs are doing their measurements during the day, then they should be getting outcomes in O1 times O2. They're each just getting measurements from their thing. So we want a measurement that's indexed by O1 cross O2 on H1 tensor H2, and that's easy to write down. We just take PX tensor QY for X and Y in O1 cross O2. And if we sum over X and Y, we get the identity operator, and these are self-adjoint projections. So how do we use this rule to get a measurement just on H1 while leaving H2 unchanged? Well, the measurement which leaves the system unchanged is just the identity operator by itself. So what we want to do is take the measurement P0 tensor 1, P1 tensor 1, and apply that to this state U. And so when we do it, it's just like what happened with measuring 1 over square root 2 E1 plus E2, right? Because when we apply P0 tensor 1 to this state, what we get is a projection down into E1 in the first coordinate, and it gives 1 over square root 2 E1 tensor E1. And the norm of that is a half again. And then the state after measurement will be E1 tensor E1. Whereas if we apply P1 tensor 1, we're going to get 1 over square root 2 E2 tensor E2. So the probability again will be a half, and the state after measurement will be E2 tensor E2. So it's very similar to the example we just did, except now they're entangled. And we did this just by measuring the first system. So what happens then if the second lab goes to do their measurement? Well, when they go to do their measurement, they're not doing it on U anymore. If they did it on U, they would get either outcome 0 or outcome 1 with probability a half. Let's say they're doing the same measurement. These 2 labs are in fierce competition to do the same measurement on their states. Okay, so they're not doing it on that state anymore because the state has changed. They're now going to do the measurement on the state E1 tensor E1 if the first lab got outcome 0, or on E2 tensor E2 if the first lab got outcome 1. So what happens if they try and measure E1 tensor E1? Well, when they do the projection onto now 1 tensor P0, they're just going to get the same state back again. And so that happens with probability 1. Whereas if they do 1 tensor P1 and they apply that to E1 tensor E1, they're going to get the 0 vector. That doesn't happen. So they actually will get outcome 0 if the first lab got outcome 0, so the state was E1 tensor E1, they get outcome 0 as well with probability 1. If the first lab got outcome 1, and so the state was E2 tensor E2, then they get outcome 1 with probability 1 now, because P1, so flipping this around, 1 tensor P1 applied to this will be the same vector, but 1 tensor P0 will be 0 applied to this vector. So they'll get outcome 1 as well with probability 1 and outcome 0 with probability 0. So when we measure H2 after measuring H1, we always get the same outcome as when we measure H1. And so this is kind of like one of the defining features of entanglement is that you do this measurement and the measurement outcomes are perfectly correlated between the two systems. So it's something that can happen with a quantum system that seems quite unusual. And we might wonder, is that something we can do with a classical system? And actually, when you think about it, maybe I should give you a chance to think about it, but time is tight. So I'll just jump right in. You can think about lots of classical systems that we don't need quantum mechanics to explain at all that have the same feature. For instance, maybe you go to, maybe you've got a job where you have to, you're a traveling salesperson selling paper to different companies, and you show up at one office and you notice one person at that office always has the same lunch as a person at a different office you drop in on. They're perfectly correlated. How does that happen? Well, maybe you find out they're married, so they prepared their lunch in the morning, and they always prepare the same lunch, so they're perfectly correlated. There's no problem there. What's special about entanglement, and we'll get into some things that actually show up, you can show up in experiments to demonstrate that this feature really is different than what you can see in the classical world or with classical explanations, is that this perfect correlation doesn't just happen for measuring with this particular measurement operator. If we use this state and we measure in a different basis, we will still get this. We will still get the measurement outcomes to be perfectly correlated, and so it happens no matter what measurement we do. And so if you think about what that means, that happens even though the state of the system is established before we actually pick what measurement we're going to do. Okay, so they end up being perfectly correlated, but they don't know, or the state has no way of knowing. I'm imagining the state is intelligent. It's not, or I guess it could be. I don't know to say that it's not, but anyway, the outcome will be perfectly correlated no matter what measurement we do, even though the state is established before we pick the measurement to do. So there is something that can be different about this. So we're going to get, basically the point of this talk is we're going to get more into that idea of why that's actually different. Now, before we do that though, I want to just talk about another feature of this measurement process that we just did, which is it seems like when we do the measurement, so I've just repeated here what happened, right? We measure H1 and leave H2 alone. We get 0 with probability of half, and then the state after measurement will be E1 tensor E1. This joint state has changed when the measurement was done. And now the portion, it seems like that means that the state in H2 has changed in a way. Okay, so measuring H1 seems to change the state for H2, even if, so I said that these could be like labs on a different floor of a building, but this was just for any two different subsystems you might have. They didn't have to be on different floors of a building. It seems possible that if you were doing a measurement on one floor of a building and it involved lots of vibration and somehow something that would really interfere with the measurement on the other floor, that measuring on one floor could change the state of the system on another floor. But what if they're in separate buildings or in separate cities or in separate galaxies? Why does measuring the state on H1 seem to change something for H2? And so this was pointed out in 1935 as kind of one of the key objections that were raised to quantum mechanics being a complete theory of the physical world in what's called the EPR paradox after Einstein, Podolsky, and Rosen. It seems like we can send signals faster than the speed of light with this measurement collapse going on. And of course, we're not supposed to be able to do that according to relativity. So something seems to be wrong with what's happened here. This has puzzled people for a long period of time. And I think it's one of the things that actually gets a lot easier to understand once you start taking an information theoretic viewpoint on what's happening, because we do have a kind of a modern resolution of this paradox, or this aspect of the paradox, which is to say that if you look at the information that's actually being sent here, no information is actually being sent, and you can quantify that. And in fact, the if you make a version of the state that is what the people in working with H2 see, it hasn't actually changed if you do that correctly. So the point is that, yes, it's true that if you measure 0 in the first system, you know what the measurement in the second system will be. But if the other system is a galaxy away, you have no way of sending that information to them. And if you did want to send that information to them, then as far as we know, that has to go at the speed of light still. So there is no way of, there really isn't actually a way of sending signals faster than the speed of light. From the point of view of the second system, when this measurement happens in the first system, they don't see the state. And so if they do the measurement, they don't know that it's actually collapsed down to E1 tensor E1 before, from the perspective of an outside observer on the whole system. They just know that they got 0 with probability 1/2 and 1 with probability 1/2 as well. So it looks the same to them. They don't actually know that the measurement was done until maybe a signal travels to them. So nonetheless, this turned out to be a very productive line of thought. It was intended in a way as an attack on quantum mechanics, and it turned out to be the key to understanding some of the features of quantum mechanics and one of the underpinnings of quantum information and quantum computation now. And really, that's because it was picked up by Bell in the 1950s and 1960s and said, he said basically, okay, we don't think we can send signals faster than the speed of light, but is there anything we can do with entanglement that we can't do with classical resources? This is a very modern way of understanding what Bell was asking for. At the time, it was more the language that they were couching it in was more along the lines of what is real and what should we use to, what is allowable in a physical theory to describe the physical world. But now we understand it in this way, that we're asking about what you can do with different resources. And entanglement might be a very interesting mathematical curiosity, but if we couldn't actually do anything in the physical world with it that couldn't be done with classical resources, it would just be that, a mathematical curiosity. So it seems like a very fruitful way to a fruitful question to ask. And to answer this, I'm going to talk about also a modern viewpoint on what Bell did. So what Bell did is called Bell inequalities, but I'm going to talk about non-local games. So in a non-local game is a simple cooperative game, can have, has to have at least 2 players, but can have more, but I'm going to talk about the 2-player version. So in this game, all that happens is a referee picks questions from question sets or input sets, IA and IB. Let's say those questions are X and Y, and sends them to 2 players, Alice and Bob, for A and B. Okay. And based on their questions that they get or inputs that they get, Alice and Bob pick outputs A and B and send them back to the referee. And based on their inputs and those outputs, the referee decides whether the players win or lose. Now, what makes this game interesting? Well, first of all, to note that whether they win or lose is based on the outputs and the inputs. So there's a function basically that says, okay, based on this pair of inputs and this pair of outputs, you win or you lose. And then second of all, Alice and Bob are working together. So they are going to cooperate to win. And they know the winning conditions in advance. They know what pairs win and what lose. So far, this game seems totally trivial. They just get the inputs and they look up what the winning outputs would be for those inputs, and they just return those, right? So what makes it difficult? Well, they're not allowed to communicate while the game is in progress. So let's say you're Alice and you've just got an input. You've got to pick your output to win. You know that the output, the winning choice of output is going to depend on the inputs X and Y. But you don't know what Y Bob got. So you have to try and pick your output so that you can maximize the chance that you will actually win this game without knowing what Y is. And Bob has to do the same thing. Oh, let me stick on this a little bit longer. So I like to think of this maybe as a game that could be offered by a casino. So maybe the casino has got a slot machine that they're going to use. They always need gimmicks for slot machines to attract players in, right? So they've got a slot machine. You sit down, and on the slot machine, something flashes on the screen, and you have to hit a button to try and win. And the gimmick is that whether you win depends on what somebody in a different part of the casino did, what button they hit based on what was shown on their screen. Now, all the rules for slot machines and stuff have to be public, right? So that's like this winning conditions known in advance. The regulators are very strict on these things. And so you could just sit down if you wanted to and have a partner, and you could sit down with the book of the rules and winning conditions and try and maximize your winning probability at this game and go into the casino and try and win. And of course, the casino is going to plan for this. And so what they can do is set the payoffs in the game so that they make a slight edge, and that they expect to make a modest amount of money as people play over time. Now let's look at a concrete version of this. Let's just say that it let's pick something that's an actual game just to make it concrete. So I'm going to pick the CHSH game after Clauser, Horn, Chimney, and Holt. Maybe the most famous non-local game. So in this game, the inputs are very simple. I think this would be a very boring slot machine. You just get a 0 or 1 shown on your screen, and the button you get to hit, there's a choice of a 0 button and a 1 button. Okay, and there's the same thing for Bob. And then whether you win or lose is whether or not the XOR of your outputs matches the AND of the inputs. So basically, if you're both shown, so if you think about what the XOR does, the XOR will be 0 if you both give the same thing, and 1 if you both get different things. So the AND will be 0 unless both X and Y are 1. So if X and Y are not both 1, then Alice and Bob want to give the same thing. But if X and Y are both 1, then they want to give different things. So that's the challenge of the game here. And if you think what can happen, like maybe the casino is trying to figure out what the payoff should be for these games. They're trying to figure out what can Alice and Bob do. Well, they can't communicate. And of course, there's going to be cheaters and so on. So maybe you put them in Faraday cages so they can't actually use a cell phone or some kind of discrete signaling device. So then they're stuck in their cage. And the best that they should be able to do is look at their question, and maybe they can determine an answer by looking at some kind of table of strategies they've worked on it out in advance. Or if they're a little more advanced, they could maybe flip a coin, generate some kind of random number to choose what output they should choose. And actually, if you want to be a little more, just to say what they could actually do, they could also choose their strategy at random before they go in. That's called shared randomness. So they could choose, they could have some kind of coin that they flip before they went to the casino as well. Okay, so if you look at strategies of this form, the best Alice and Bob can do is to win with 75% probability. They can get to that if they just always output 0, because then this is assuming, by the way, that both X and Y are picked with a uniform probability distribution. So then 75% get, when they both get a 1, they lose, okay? And you can show pretty easily that's the best you can do. So what if they actually share an entangled strategy? So now the casino is looking at it. They've got these strange players who are coming to the casino with giant refrigerators, essentially, and very complicated measurement devices. But that's okay. They get locked in the Faraday cage. They're supposedly not able to communicate anymore. And we know that even if they're entangled, they're not supposed to be able to send information with that, right? So they really aren't communicating. They're not getting around that no communication barrier. It turns out you can show that they can win with 85% probability. So if the casino was making their payoffs based on this idea that the best they could do is 75%, you could beat the casino with entangled strategies. A casino has yet to offer this game as far as I'm aware. So if they do, they're probably the cat's out of the bag. This has been known for a long time that you can do this, so they're probably not going to give you, set their payoff so that you can win with entanglement. But if a casino could be found to offer this game, you could potentially get an advantage with entanglement. So that's the idea. With these non-local games, we have a very simple scenario, and with entanglement, we can actually get an advantage over what we would expect to do classically. So the answer to Bell's question is that yes, you can do something with entanglement that you can't do if you just take a classical description of reality. And the interesting thing about this, when you talk about a lot of things in quantum computation, this is slowly changing, but most of the things we talk about are theoretical. They're things we hope to do someday. But with Bell inequalities and these non-local games, this has been demonstrated repeatedly in experiments. You can do this. So starting with Friedman and Clauser back in 1972, but then in a sequence of experiments, so to kind of basically focus in and really prove that you can do it with no communication and closing other loopholes that people might imagine in the experiments, to show that this feature of entanglement really does exist in our physical world. So the main loophole you have to close is, how do you guarantee that Alice and Bob can't communicate? This is called the locality loophole. And what you can do is you can say, if you really want to be very strict about this, you can say, we're going to separate them so far apart that we're going to look at the time that it would take for a signal to travel between them at the speed of light. And then we'll try and have them get their question and return their answer faster than such a signal could travel. So, so people started trying to actually, so I should say actually, so what that would mean is then you would get a result that would say either entanglement exists like either there is either the classical description of reality is insufficient. We can't necessarily say that it would have to be the quantum mechanical description I gave so far, but we can say the classical description is insufficient, or relativity is wrong. One of those two things is broken then, if we can make an experiment like that. And so that line of experiments doing just that started with Aspect in 1982. And there's been better and better versions of them. The one I often quote is this Salart et al. In 2008 that had an 18-kilometer separation between the where the entanglement was generated and where the measurement was done to play the game, so to speak. And that gives you 60 microseconds to play your game, which is enough apparently. Apparently, it's actually lots of time if you're an experimentalist. So and this line of experiments has continued actually in 2015. There were a very kind of celebrated set of experiments that closed pretty much all the major loopholes that people had pointed out, and that didn't require very convoluted. So there are still some you can never really get rid of all loopholes, but the ones that are left require fairly convoluted explanations to explain why it would nature should behave like that, and still allow this violation of these Bell inequalities. Okay. Now, what can Alice and Bob do in a non-local game according to quantum mechanics? So we're back to the general framework here. So to an outside observer just looking at this, their behavior would be completely described by the probability PAB XY, which would be the probability they output A and B on inputs X and Y. So this is a family of probability distributions here. And according to the rules of quantum mechanics that I mentioned already, Alice and Bob can get to PABXY if there are Hilbert spaces HA and HB for their local systems, and then a state in the joint system HA tensor HB, and then measurements, because they got to figure out these outputs, and they're going to do that by measuring their system. When you think about something, they interact with the system and then get some answer. That's a measurement in a very abstract sense. So there'll be some measurement operator then on their system. So PXA acting on HA and QYB acting on HB, such that so this works out to be, according to the rules we mentioned, the probability that we get A and B on inputs X and Y. Because these are projections, this is the same thing as the norm squared of PXA QYB applied to U. So just say PABXY equals the inner product of U with PXA tensor QYB of U. Okay, so what we would like to know is, so let's say we look at the set of P's which are of this form for some Hilbert spaces, vectors U, operators PXA and QYB. So this is called the set of quantum correlations indexed by the given set of inputs and outputs. We'd like to describe this set because that captures what Alice and Bob can do with entanglement. Okay. So now going forward, it's kind of annoying to say CQ, OA, OB, IA, IB all the time. And so usually what we do is we just say, well, really what matters is the number of inputs and outputs. So we'll just let M be the number of outputs and N be the number of inputs and call it CQMN. And actually a lot of the time what we do is we just forget about M and N altogether. So whenever you see CQ, there's some M and N there. We're talking about it for some number of measurements. And so what we'd like to do is to describe these sets CQ. And while there's been all this stuff going on the experimental side, this kind of the understanding what's going on the math side has happened much more slowly. So it's only been in the last few years that we've been able to kind of to get some idea of what's going on. So of course, when we talk about describing the set, that could mean lots of different things. I mean, I've described it right here. So what's not good enough about this, right? So to pin down what we would like in a description, we can talk about the membership problem for quantum correlations, which is given some M and some N and some P, determine if P actually belongs to CQ. A description that doesn't answer this question doesn't allow us to do very much with it. So, and so this gives us a very kind of generic way of talking about possible descriptions of the set. By the way, to make this practical, we actually we can't really talk about all elements of R in a computer program. So we should actually replace R with some computable field when we actually pose this membership problem. Like it could be Q, or it could be like the two fields I'm going to talk about are Q and Q adjoint roots of unity. So
William, allow me to ask a question. I was wondering whether or not you have to work in a finite field because of what you said earlier about, if you wanted to do this in a computer that it could only store finitely many numbers.
So usually the way it's like, excuse me, sorry, it's like you pose the problem first and then imagine like when you talk about factoring a number, right? So you can talk about the problem of factoring a number for any number. You don't have to put a bound on it ahead of time. But then if you want to factor a number with a trillion digits, you need to build a computer that's large enough to hold. Well, I guess a trillion digits isn't actually that much just to hold the input, but the point stands. You need to build a computer big enough to actually then hold your problem. So we can just talk about it for any computable field. We don't need to talk about like a finite subset of a field just for inputs to this problem. But then it's understood that the Turing machine or the abstract computer that we're thinking about, if we were to try and translate into a physical computer, we would need to adapt that physical computer based on the actual input we get.
Thank you.
Yeah. Now how are we doing on time? We go until 4:05, right?
4:05, 4:10, so 10, 15 minutes.
And maybe I'll try and say this. This isn't too long. Okay. So so I want to talk about, there is one situation to understand the history of this membership problem here. There is one situation in which we can answer this, and that was in the case of unbiased correlations. So for unbiased correlations, those just mean correlations where if you just look at what Alice does, so take PA XY with Bob outputting 0 plus PA XY with Bob outputting 1, then you always get a half. And similarly for what Bob does independent of what Alice does, you always get a half. We can analyze, we can answer the membership problem for that. Maybe I'll skip some of the technical details in here just to make sure we have enough time. So it turns out that, no, I think we'll have enough time. This should be short. If you just look at this quantity dxy that I've written down, you can use this these equalities here to translate. You can turn a p11 xy into a half p10 xy based on this equality. And so you can actually just turn dxy into some constant times p00 xy, or just any of these individual quantities. You can recover each of these from just dxy if you know that these equalities hold. And also note that actually how this works is that I've got a plus, so I've got plus p00 and plus p11. So, and I've got minus p01 and minus p10. So the sign out here depends on the XOR of the outputs. So these are called sometimes XOR correlations. And these correlations are all we need to analyze games where the winning condition depends on the XOR of the outputs. The reason, okay, this is maybe the part I'll skip. If you just go through and look at, if you imagine that P actually had a quantum model, and then you calculated dxy from that, you would get something which looks like a unitary, right? If you take two orthogonal projections, px0 and px1, and you look at their difference, two orthogonal projections that sum to the identity, then that will be a unitary. So it's a unitary times a vector and another unitary times a vector. So these are two unit vectors here for this dxy. So what you get is that dxy is actually the inner product between a collection of unit vectors vx and wy. And then what Cyrilson showed in 85 as part of founding the study of quantum correlations is that P belongs to CQ to the unbiased part of CQ. I should have really put that in this. I was hoping, I guess, that would be understood from this being in the slide, but I should be very clear about that. This is only for unbiased correlations. So P belongs to CQ if and only if dxy is an inner product of vectors Vx times Wy for some unit vectors Vx and Wy. And I should say, I always kind of end up not putting in the quantifiers just to save space on the slide. So what this means is that for you fix D ahead of time. So it's a list of numbers indexed by X and Y, which are from the input sets. And then there has to exist some collection of vectors Vx and Wy such that dxy equals Vx times Wy for all X and Y, just to make sure that's clear. Okay, so what that means is then, if you look at inner products between a collection of vectors, that's a Graham matrix or semi-definite matrix. And so what we want to be is the upper right-hand corner of a Graham matrix. And you can decide whether something's the upper right-hand corner of a Graham matrix in a number of different ways. So that allows you to decide the membership problem for unbiased correlations. Oh, right. So what about all correlations? So the problem here is that, well, let me just recall how we defined a correlation, right? P was in CQ if and only if P was PABXY was a set of inner products like this for some operators PXA and QYB and some state U. For U in, now I never really got into this, but for CQ, we actually picked the HAs and HBs to be finite dimensional. It corresponds in quantum information with the idea of quantum systems that we can actually control. We can only really control the finitely many degrees of freedom. So this is what we might hope to build in the lab, more or less, I should say. And that means that if we're given P, what we can do is just start searching through finite dimensional Hilbert spaces. We got a solution. We got equations here in real variables, and there are algorithms for deciding any set of equations in real variables. They run very, very slow, but they do exist. And so this is a problem where we can just start searching through finite dimensional Hilbert spaces, and for each pair of finite dimensional Hilbert spaces, decide whether or not there is a U and a PX collection of PXAs and a collection of QYBs, such that we get P from that collection. If we were dealing with unbiased correlations, the way Cyrilson proves his theorem is by showing that you can actually get every P that is in CQ with Hilbert spaces of dimension at most 2 to the floor of n over 2, where n is the number of questions. However, there's no such bound for general correlations. So we might start to search, and our search is never going to end. So when you have a problem like this, a computational problem, where you can search through the solution space, and if it is in your set, you will find it eventually, but which you never have a stopping point. You never have a way of saying, oh, it's not in the set. The set of languages that have algorithms like that is called RE, recursively enumerable. So what we get at this point is that membership in this set is recursively enumerable. Okay, but not, from what we've seen so far, decidable. We don't know if there's a way to actually say there's an algorithm which will always end and which will tell us either yes or no, it's in it or it's not. Now, another complication here is that CQ is not the only set of quantum correlations to consider. So I said that we should look at finite dimensional Hilbert spaces, but we could look at infinite dimensional ones. That set's called CQS. And we could look at the closure of these sets. So if you were to look at a set like one of these ones I wrote down for a finite dimensional Hilbert space, it would be a closed set. But when you have no bound on the dimension, there's no guarantee the set will be closed. So we don't know if it's closed or not. So we can just take the closure and call that a new set of correlations. And it turns out from some facts and operator algebras that this is the same thing as taking the closure of this set CQS, which is nice. We don't have to consider two different closures. It's very natural to consider the closure because these are the things we can get as limits of finite dimensional strategies. And if we can get, you know, it might just be good enough for what we want to get close enough to a correlation. So maybe we can think of these as, you know, it's kind of, they're the correlations where it's just how much money do we want to pay to implement them. We can get arbitrarily close to anything in this set with a finite dimensional system. And then finally, there is another axiom for how we can combine systems called the commuting operator axiom. So in this axiom, we replace a tensor product with just a single Hilbert space. And rather than asking that these operators act on these kind of individual tensor factors, we just say that the operators act on this single Hilbert space H, but they have to commute. And that's you can show that if that's satisfied, then Alice and Bob wouldn't be able to communicate either. So it's also a model in which they can't communicate. If you have a finite dimensional Hilbert space, you can show that that any correlation you can get with a commuting operator in this commuting operator model, you can also get in the tensor product model. You can just take decompositions of the space, which look like tensor products. But in infinite dimensional Hilbert spaces, that's not always possible. So you have this question, if you look at the set CQC of correlations that you get from commuting operator correlations, is it the same as CQ or CQS or CQA? One thing you can say is that all these sets are convex, and they give a hierarchy here of correlations. You get CQ contained in a set of CQS, contained in a set of CQA, contained in a set of CQC. Now, what's the history of these? What's known about these? Well, Cyrilson introduced a study of these, and in a 93 paper, he claimed that it's a little ambiguous whether he was actually studying CQS or CQ, but he claimed that CQS is equal to CQC, or maybe it was CQ equal to CQC. This is in the prehistory of the subject. And so he has a description. I should say, by the way, Cyrilson was kind of an amazing mathematician who did a lot of stuff in different areas of analysis, and unfortunately passed away last year. But when he was doing this, he was way ahead of his time. Nobody else, he has a description of what of his work in this area on his website, where he said basically nobody really cared about it. And so in 2008, I forgot to include the year here, but in 2008, Nevescas, Peronio, and Athene started looking at correlation sets. And I should say maybe around by that point, quantum computation kind of as a subject was well underway, and there was a lot more interest in these objects at that point. And so they noticed that if you wanted to show that if P is not in CQC, you could use what are called SDP hierarchy methods to prove that. So basically, you can find a list of semi-definite programs such that if P is not in CQC, by looking at the optimal values of those, eventually one of those will tell you that P is not in CQC. But you have the same problem that you have for membership in CQ, that there's no obvious way to know when to stop looking at the hierarchy if P is actually in CQC. So we get from that membership in CQC is co-RE. And if that means that if CQ was equal to CQC, if Cyrilson's claim, the stronger one, was correct, we could actually decide membership in these sets. because on one hand, we look for finite dimensional strategies to prove that our correlation is actually in the set. On the other hand, we try and prove that it's not inside. And so the way I've heard it is that they were looking at this. They found these STP hierarchy methods for this problem and thought maybe we solved the problem. They got in touch with Cyrilson to ask about this claim, which, as I said, was a claim in a paper but was not proved. And he ended up withdrawing the claim. And to say, just to add a little more of the detail he gives there. So basically, the 93 paper was kind of he wrote down what kind of some notes that he knew, things that he thought he knew at the time, and then he actually left the field. So he was, I think, something that's very understandable in the context of the lack of interest that was in the subject at the time that this happened. But what happened out of that was people realized these Cyrilson problems, as it became known, were very interesting. Whether or not any of these sets, CQ or CQS or CQA, were equal to CQC. And actually, then people notice as well that out of these, the last pair, CQA equal to CQC, is equivalent to the Kahn embedding problem. This was noticed first, that the Kahn embedding problem being true would imply the equality here. So this was noticed by Fritz and also by Young and Nevesquez, Palazuelos, Perez Garcia, Schultz, and Werner. And then Ozawa proved that actually the equality here is equivalent to the Kahn embedding problem. So I don't want to get too much into the Kahn embedding, or at all into the Kahn embedding problem. From the point of view of this talk, this is the important question. But I should say this problem has been a notorious problem in operator algebras, starting with a simple question of Kahn that turned into to have many different equivalent formulations in other areas, and this being one of them. There's an intuitive reason why this is the most important equality to know here, which is that we don't know whether or not CQ and CQS are closed at this point in the talk, I should say, but CQA is a closed convex set, and so is CQC. You can see there, just using kind of standard methods in analysis, that it's closed. And so when you talk about separating closed convex sets, if they are different, they can be separated by a hyperplane. And a hyperplane more or less corresponds to a game. And so if these two are separated, that would mean there is a non-local game where CQC strategies have an advantage over CQA strategies. And that would mean, because CQC strategies are necessarily, if they're different from CQA strategies, they're necessarily infinite dimensional. That would mean that you could imagine an experiment where you could demonstrate that nature is intrinsically infinite dimensional. In the same way that you demonstrated in a Bell inequality in experiment that entanglement or that classical correlations are insufficient to describe reality, which we take as evidence that entanglement exists. So you could show that there's something that's kind of intrinsically infinite dimensional in nature. We don't think it's possible to do such an experiment. We think that everything in nature probably is described by correlations in CQA, but separating these two sets would allow us to say that such experiments are mathematically possible. Okay, so this was a mystery for a while as to what was going on here, but just in the last few years, we started to get some answers. So in 2016, we found that CQC is not equal to CQS, which means there are commuting operator correlations which aren't tensor product correlations. So these two axioms, the commuting operator axiom and the tensor product axiom, are actually different. And then also we found that actually CQA is not equal to CQS, which means these two sets aren't actually closed. So we do really need to talk about CQA if we want a closed set. Coladangelo and Stark in 2018 proved that CQS and CQ are different. So there are infinite dimensional tensor product correlations, which aren't finite dimensional. And finally, the big one last year, G, Natarjan, Vidic, Wright, and Ewan proved that CQA is not equal to CQC, so resolving this Kahn embedding conjecture. So we actually know that all these sets are different now. So as opposed to Cyrilson's original idea that these were all the same, it turns out to be exactly the opposite. But if you'd never asked he created the study of these things, we would never have known about these questions if he hadn't created them. Okay, so now back to the membership problem, just to wrap up here. Along with separating these sets, interestingly, I think this is kind of interesting because you wouldn't look at this and say that the membership problem should be involved here, but we've actually been able to resolve the difficulty of the membership problem at the same time. And the methods, they actually end up being kind of connected. So first of all, we found that membership in CQC is undecidable and actually equal to co-RE. And then that membership in CQA is undecidable and contains co-RE. I'm just going to go through the highlights here. So then the interesting part here is that what G et al. Did is that they showed that membership in the sets CQ actually contains CQ, CQS, and CQA actually contains RE. So that tells us that in particular that membership in CQ is RE, equal to RE because it was contained in RE. So it's not possible for the Kahn embedding conjecture to hold. And this is how they actually proved this. They proved it by proving the membership problem is undecidable. They actually prove a stronger result, which I'll just skim over here. So it's by considering this membership problem that they were actually able to separate the sets. Okay. And I'll say just about this, that work in this area has actually been continuing. If you look at the membership problem for CQA, you can actually show that it's larger than both RE and co-RE. Okay, so I'm going to just skip over this. I don't want to take up too much time here. I'll say that one of the things that we've been continuing to do is to show that for large enough M and N, that membership in these sets is actually undecidable if you fix the number of measurements as well. And this is interesting because if you imagine, so these membership problems here are all allowing the number of questions and answers to vary. And that's if you think about, you want to model a Turing, what you essentially want to do is take a Turing machine and model for each Turing machine and input. You're trying to reduce membership problems to the halting problem. So for each Turing machine and input, you want to reduce it to a correlation. And you need some part of that correlation to vary with the input to the Turing machine. And often part of what varies is the size of the correlation. So we can actually do it with a fixed number of measurements now, just a paper we came up with this year with Hong-Hao Fu and Carl Miller. And this requires making the field a little bit larger than some of the other results we mentioned, because something has to vary according with this input. So what varies is we can't just talk about rational numbers. We need to talk about roots of unity getting very close to 1. And what that means is that if you think about these individual sets not allowing M and N to vary, but just the individual sets, they also can't have very nice descriptions. So anyway, I'll stop there. I don't want to go too much over my time. So thanks.
Thanks so much, William, for a wonderful talk. Do we have any questions for William?
I can ask one on this last slide. When you talk about F equals Q plus roots of unity, do you have bounds on the roots of unity depending on M and N, or is it all roots of unity?
So what has to so what varies there is so we need to think about higher and higher roots of unity for larger and larger inputs to the Turing machine that we're kind of reducing this membership problem to. So it really does need to be all roots of unity for every. So this is for large enough M and N. So for every M and N where this results apply, we need all roots of unity. But for a fixed, that is to say, so we're taking an instance of the halting problem, so a Turing machine plus an input, and reducing it to a membership of a correlation in one of these sets. It's a polynomial relation between the size of the input and the excuse me, I think it's actually a polynomial relationship between the value of the input to the root of unity we need to take. Yeah, so it's very explicit how the reduction works, but you need those roots of unity in there of arbitrary orders.
Okay, thank you.
And we very much like to be able to do that without that in there. And that's related to whether you can do an approximate membership, a version of this theorem for approximate membership. So.
Any more questions for William?
Yeah, I just wanted to make sure that I understood that the JNVWY, where they proved that QCQ was not equal to CQA, that they actually that's what they proved, and they didn't do a head-on resolution of the Kahn embedding problem. Is that correct?
What they actually prove is something different, but you can get this this difference. They didn't do either. So what they proved is that if you go to non-local games, they prove that it is actually, I've got it right here. Where is it? So the specific thing they prove is this stronger result. So there's a family of games such that in that game, so the non-local games that I talked about, in two-player games, exactly like I talked about, such that the optimal quantum winning probability is either 1 or less than or equal to a half. And then the problem of deciding whether those game, which of these two is the case, is RE hard. And so you can, because a game can be thought of as a linear function on the set of correlations, you can turn that into undecidability of the membership problem. You also get, because Kahn embedding would also imply the decidability of that problem for the same reason that the membership problem would be decidable. You could either use a finite search through finite dimensional strategies or a STP hierarchy method coming down from above. You could decide this problem if Kahn embedding was, well, if these correlation sets were the same, you could decide this this membership problem. So that forces the correlation sets to be different. So forcing the correlation sets to be different, they do that indirectly, but it's through this result about games. So the name of their paper is called MIP star equals RE. MIP star being the complexity class that is the languages for which there are proof systems which are built out of games. But it's exactly that result about games that I mentioned.
Okay, so it's sort of in this context, but not really, is what you're telling me.
I would say it's in this context. It's very standard, like all for people in this field, that would be a standard translation between the two. So whether you call that context or not, it's up to you. If you want to say it's a different context, that's fine too. Yeah.
Okay, no, I'm happy.
Yeah.
I'm happy.
Yeah.
Thank you.
Any more questions? Let's all thank William again. William, thanks so much.
Thanks.